Hello, welcome back to the next class of design of RC structural elements. Here it is design of beams. So let me go with the next problem. The problem goes like this. Design a beam of effective span 6 meter to support a total working load of 12 kilonewton per meter, including the self weight of the beam. The width of the beam is limited to 250 millimeter. Use M20 concrete and Fe415 steel. See, I am going to divide the problem into 4 or 5 different steps based on the requirement. One is calculation of design moment. MUD. Next, calculation of effective depth, D. Next, calculation of area of tension steel, AST. Next is check for shear, or in other words you can also call it as design for shear, and it is check for deflection. So these are the steps. So I have divided the problem into. So the problem goes like this. Design a beam of effective span 6 meter to support a total working load of 12 kilonewton per meter. Okay. So it is given as effective span. So take the value as it is. So 12 kilonewton per meter including the self weight of the beam. Say when they say it is service load, working load, service load or just load is one and the same. Okay. And this includes self weight of the beam itself. Of course the beam weighs some weight. Okay, that should be included. If it says the self weight is not included, because it includes the self weight, you don't have to add the self weight once again. So the width of the beam is limited to 250 millimeter. The width of the beam is fixed. We cannot change it. Use M20 concrete and Fe 415 steel. So let me go with the first step. Calculation of design moment MUD. That is calculation of design moment MUD. So what is the service load given? Service load or working load? So the working load given is W equal to 12 kilonewton per meter. So we need design load. Therefore, design load, I am going to call this as WUD. I am going to multiply W value with a load factor. What is the value of the load factor? That is 1.5, as we discussed in the previous example. Multiplied by W, that is equal to 1.5 multiplied by 12, that is equal to 18 kilonewton per meter. This is the design load or factored load or ultimate load, which have called as WUD. So if I take the beam of effective span 6 meter, I am going to call this as L suffix E, and the design load is WUD equal to 18 kilonewton per meter. Okay. So I have this. Now I need to calculate the design moment. Therefore, the design moment, I am going to call that design moment as MUD equal to WUD L square by 8. That is equal to 18 multiplied by L is the effective span. Okay. So I am going to call this as LE divided by 8. So the value of MUD equal to, that is 4, 9, 20, that is 36, 2.25, 72, 81 kilonewton meter. Okay. So let me cross check it. That is 81 kilonewton meter is the design moment for which we need to design the section. So this part is over. That is calculation of design moment MUD is over. The next step is calculation of effective depth D. So calculation of effective depth D. See, whenever we design a section, so normally we start with the section as a balanced section, okay, and we are going to make use of the formula given on page number 96 under 1.1c, that is mu limit to start with we are going to find out the depth, the effective depth as depth for a balanced section. For a balanced section. So as per 1.1c on page 96, so we have mu limit equal to it is 0.36 FCK XU max by D 1 minus 0.42 XU max by D. I think there is something wrong here. That is FCK BD square. That is FCK 0.36 here. FCK BD square. So this is the formula. This is as per 1.1c. So annexure G, page number 96 of the code book. So for a balanced section, for Fe 415 steel, XU max by D equal to how much? 0.48. This is as per 38.1 page 70 of the code book. Okay. So in this value is substituted here, and FCK, of course, for M20 concrete it is 20, B is 250, and for mu limit value I am going to substitute the value of MUD. This is the design moment due to external load, and I am equating this moment to the limiting moment of the section, that is the moment of resistance of the section. Okay. So by substituting the value of MUD for mu limit in the above equation, we get so for mu limit I am going to substitute 81, and I am going to convert the value into Newton millimeter. That is equal to 0.36, and XU max by D is 0.48. 1 minus 0.42 multiplied by 0.48, and FCK is 20 and B is 250 and D square, and D is the value we need to find out. On further simplification, we are going to get the value, this value equal to 689.82 D square, that is 81 multiplied by 10 to the power of 6. Therefore, D equal to 343 millimeter. So that is the minimum effective depth required for a balanced section. Okay. So if this is the effective depth, if you are providing the section like this, and if you have reinforcements here, and we don't know how many reinforcements we are going to provide, that is tension reinforcement I am talking about, and we are going to provide stirrups like this, and I am going to provide 2 anchor bars here. So the minimum required depth D is 343 millimeter. 343 millimeter. So what is the total depth D? This is the total depth D. So total depth is given by effective depth plus effective cover. Effective cover depends on the diameter of the stirrups, diameter of the main bar, and the clear cover. If you open page number 47 of the code book, please open it. Please open. On page number 47 of the code book, if you refer table 16, so for mild exposure of the concrete beam, nominal concrete cover in millimeter not less than 20 millimeter. Okay? So from table 16, from table 16, page 47, so for mild exposure, minimum clear cover equal to 20 millimeter. What it means? We are going to give a cover of 20 millimeter. Okay? So that clear cover should be for the stirrups. So let us provide 16 millimeter dia main bars and 8 mm dia stirrups. Okay. So once we provide that, what is going to be the effective cover? Effective cover we are going to measure from the compression edge to the centroid of the tension steel. So what it is? Effective cover is 20 millimeter, that is a clear cover, plus the diameter of the stirrup, that is 8 millimeter, plus half the diameter of the main bar. So what is the diameter of the main bar we are using? We are using 16 millimeter. So 16 millimeter by 2. So that is going to be the effective cover. Therefore, effective cover equal to clear cover plus diameter of the stirrups plus half the diameter of the main bar. How much it is? That is equal to 36 millimeter is the effective cover. Okay? Therefore, total depth equal to small d plus that is the minimum depth required, minimum effective depth required, plus the effective cover that is equal to 343 plus 36, that is equal to, so it is 379 millimeter. That is the total depth, minimum total depth required. But we are not going to provide this much. Instead, we say 400 millimeter. We are going to provide an overall depth of 400 millimeter. That is the total depth. Therefore, we shall provide 400 millimeter depth beam. Okay. Therefore, actual effective depth. Actual effective depth. Remember, it was 343 required, 36 is the effective cover, add it, that is the minimum overall depth required, but we are not going to provide this fractional value. Instead, we are going to go and increase the depth to the next higher number. So, it turns out to be 400 millimeter, the overall depth. Once we have the overall depth, then we have to get the actual effective depth provided. Therefore, actual effective depth provided, I am going to call that as D, actual overall depth minus the effective cover 36 millimeter, that is equal to D equal to 364 millimeter is the actual effective depth we are providing. Required is 343, okay, for a balanced section, but we are providing actual effective depth of 364 millimeter, which is greater than 343. So, that is okay. So, we will go with the next step. So, the next step is calculation of area of tension steel. Calculation of area of tension steel, AST. So, in this case what happens is, because we are providing an effective depth of 364 millimeter, which is greater than the required of 343 millimeter for a balanced section, the section is going to be under reinforced. See, as I discussed in the previous class, so to resist a given moment due to the external load, so we need moment of resistance of the section. Okay, that moment of resistance is given by compressive force or tensile force, because numerically they are the same, multiplied by the lever arm. Okay. So, if I take tensile force, it is going to be area of steel multiplied by the design strength of steel, which is 0.87 Fy. multiplied by the lever arm. That is equal to the moment we are going to apply due to or through the load. Okay. So we got some value for a balance section. Once you increase the depth, so what happens to the lever arm? Lever arm increases. As a result, the moment of resistance is given by, of course, compressive or tensile force multiplied by the increased lever arm. Okay. To resist the same moment, once you increase the lever arm, the area of steel required will be reduced. So once the area of steel required reduces, then it is not going to be a balance section anymore. Instead, it is going to be an under reinforced section. Okay. So it is not going to be unsafe. It is going to be under reinforced. Okay. So once it is under reinforced, to find out the area of steel for an under reinforced section, the formula we can make use of is on page number 96. You have the formula under 1.1.b. So what is the formula we have? That is mu equal to 0.87 Fy AST multiplied by 1 minus of 0 AST Fy divided by BD FCK. Okay. Because the section is under reinforced, we can make use of the formula mu equal to 0.87 Fy ASTD minus AST Fy multiplied by BD FCK. So this is as per 1.11-1B page 96 of the code book. Okay. So that is the formula I am going to make use of. So in this formula for mu, I am going to put the design bending moment. So by substituting the value of MUD for mu in the above equation, we get 81 multiplied by 10 to the power of 6, that is equal to 0.87415 into AST, that is the one we don't know, and that is the one we are going to calculate. Then what is D? D is not 343 millimeter which we calculated for a balance section. Instead, we have to provide the actual depth of actual effective depth of the beam we are providing. So what is the actual effective depth we are providing? That is 364 multiplied by 1 minus AST, yes, we don't know yet. Fy is 415, B is 250, multiplied by D is again 364, and FCK is 20. Okay. So what is the unknown here? AST is the unknown. So finally the equation reduces to AST square minus 4385.12 AST plus 27.0.27 into 10 to the power of 4, that is equal to 0. So this is the equation in the form of ax square plus bx plus c, wherein the solution is x equal to minus b plus or minus square root of b square minus 4ac divided by 2a. So by using that expression, so we are going to get the value of AST equal to 742 millimeter square. Okay, 742 millimeter. So in this case, that is the minimum tension steel area required. That is, if you have the beam like this, so these are AST bars. Okay. So because we are providing, if you remember, we adopted 16 mm diameter main tension bars because we are providing 16 mm dia bars. Number of bars equal to total area of the steel required divided by area of each bar. That is equal to 742. So area of each bar is pi by 4, 16 square. So number of bars is 3.69. Of course, we cannot provide 3.69 bars. Instead, we go ahead and provide 4 bars. Say 4 bars. Therefore, we shall provide 4 bars of 16 millimeter dia. Okay, 4 bars of 16 millimeter dia. Now, the actual area of steel provided is going to be more than this. Therefore, actual area of tension steel provided equal to 4, because we are providing 4 bars multiplied by area of each bar. That is equal to 804.25. Let me check. 804.25 millimeter square. Okay. That is the area of steel provided. If you open page number 47 of the code book, please open it. If you open page number 47 and 46, so 46 second column at the end under 26.5.1.1 tension reinforcement, it says minimum reinforcement. It says the minimum area of tension reinforcement shall be not less than that given by the following equation. So what is that following equation? That is AS divided by BD equal to 0.85 Fy. Okay, that condition should be satisfied. So to check for minimum area of steel, minimum area of steel. So as per 26.5.1.1, so minimum area of, I say, tension steel. Tension steel. So page 47, we have AS by BD equal to 0.85 divided by Fy. Okay, AS divided by BD equal to 0.85 divided by Fy, or that can be written as AS equal to 0.85 BD divided by Fy. Okay, so for this AS, we are going to call this as AST minimum. That's what I am going to call this. If you want, you can retain this as AS, but I am going to call this as minimum tensile steel required. That is equal to 0.85 into 250 into 364 divided by 450. Okay. So that turns out to be 186.4 millimeters square. (186.4 millimeter square). Okay. So AST provided here, AST provided here, AST is greater than AST minimum. Therefore, okay. What it means is, in case if we get this value less than 186.4, say 150 millimeter square, in such case we have to provide at least this much, 186.4 millimeter square. But in reality we are providing 804.25 millimeter square, and the minimum required is 186.4, and we are providing the area of reinforcement more than minimum required, that is AST greater than AST minimum. Therefore, okay. Is it clear to you? So once this is done, the next step is check for shear, or in other words, design for shear. Okay. This is calculation of area of tension steel AST. So far what we have done is we have calculated the area of steel required in the tension zone, and also we calculated number of bars, 16 millimeter diameter bars, which turned out to be 4 numbers. Afterwards we checked for minimum tension steel and maximum tension steel as per the codal recommendation, and we made sure that the actual area of steel provided is within the limits of AST minimum and AST maximum. The next step is the curtailment of tension steel. Curtailment of tension reinforcement or steel. So write down if this is the beam okay, supported over two supports, okay, and 6 meter is given as the effective span. The same 6 meter I am going to assume as the span between the centers of support. Remember, so when it comes to effective span, it is always clear span plus one effective depth and the distance between centers of supports. So lesser of those two values. But in the problem, what is given is the effective span is 6 meter. Okay. So in such cases, we are going to take the central distance, that is the distance between the centers of two supports as 6 meter, and I am going to write that here, and we are providing tension reinforcement in the tension zone like this. Is it not? We got 4 bars of 60 millimeter diameter. So if I take the cross section, I am going to show 2 cross sections. Okay, I am going to call this as section AA. This is section AA. Section AA. And these are the reinforcements at section AA. And this I am going to show as section BB. Okay. So this is section BB. But I am not showing the reinforcement, number of reinforcements yet. You are going to know why. So if this is the support, it will have certain width. Support width is not given. So if I extend this like this, and if I draw bending moment diagram for this simply supported beam under uniformly distributed load, so I am going to get the bending moment diagram like this. And of course, I am going to get maximum bending moment at the midsection of magnitude WL square by 8. If I call this as L, E, that is the effective span, at a distance of LE by 7, that is at a distance of LE by 7 means LE is the distance between these two supports, okay, and at that distance, at a distance of LE by 7 from this support, the bending moment here will be about 50% of the maximum bending moment. So what we can do is, we can reduce the number of bars required by 50%. Here if I take a section, yes, 4 bars. So about 1/7 of the span. So theoretically I can cut off 2 bars. I am going to take out 2 bars. I am going to retain only these 2 bars. and middle 2 bars I am going to end theoretically here. But the code says, see, we should not cut the bars at the theoretical cutoff point. From the theoretical cutoff point, we have to extend the bar for a distance equal to 12 times the diameter of the bar or 1 effective depth, whichever is greater. So if you do that, we are not going to cut the bar here at this point. Instead, we are going to extend this for certain distance. There we are going to cut. Okay. So here up to here we have 4 bars. So beyond this point we have only 2 bars. Here and here we have got 2 bars. So when you consider this section, you will see only 2 bars. And this is the actual cutoff point. This is the actual cutoff point. This is the theoretical cutoff point. But the code says you will have to extend the bar for a distance equal to 12d or 1 effective depth, whichever is greater, beyond the theoretical cutoff point. Okay. Then you cut the bar. Curtailing is nothing but ending the bar. Okay. So we will do that. So we can curtail %50 of the bars at 1/7 of the span from each support, However, that is the theoretical cutoff point. That is the theoretical cutoff point. So what is the theoretical cutoff point? Therefore, theoretical cutoff point equal to LE by 7, that is equal to, what is LE? 6 meter, that is 6000 millimeter by 7. Okay. So that is equal to 857 millimeter from the center of the support, that is from this center it is 857 millimeter, that is the theoretical cutoff point. Okay. So and similarly we do on this side as well. However, the bars are extended for a distance equal to higher of the following two values. What are those values? That is 12 times the dia of the bar, 12D. Here we are using 16 millimeter diameter bar, that is we are cutting off 16 millimeter dia bars, and one effective depth. So instead of D I write dia, then one effective depth. That is D equal to 364 millimeter is the effective depth, and higher of those two values, that is 26.2.31, page 44. Okay. So 364 millimeter is the distance to which we are going to extend those two bars from the theoretical cutoff point. Okay. So this is the value. Therefore, actual cutoff point from the center of the support equal to, so it is 857 from the center of the support to the theoretical cutoff point, 857 minus, so we are going to extend that for a distance equal to 364, that is equal to 493 millimeter. Okay, say 490 millimeter. What it means? So we can cut the bar such that this distance, the actual cutoff point from the center of the support is 490 millimeter on both sides. Is it clear to you? So this completes this step, calculation of area of tension steel AST. Then what is the next step? Check for shear. So please write down check for shear. So what is the reaction? 50% of the load will go to this point, this support, and the remaining 50% to this support. So the reaction will be 54 kilonewton, and here also it is 54 kilonewton. Okay, this is WUD. So if I draw the shear force diagram, so the shear force diagram will be like this. So this is VUD, that is equal to 54 kilonewton. Similarly, here it is 54 kilonewton. Okay. So if you remember the first class, what happens is, this is a beam. Okay, and this is a support on one side, and from the center of the support I have taken this distance. This distance is 6 meter. Okay. So whatever the reaction here is the shear force, that is the maximum shear force. However, as I explained in the first class on shear, we should not consider this face of the support. Instead, we should go for a distance equal to d from the face of the support. Okay, and that's where you must consider. Okay, and take that section and come here and find out what is the shear force here. That is at a distance of 1d plus half the width, that is d plus half the width of the support is the distance. So there you can find out what is the shear force, that is the design shear force. Okay. So for this shear, you need to provide shear reinforcement, and this shear will be less than this shear. But normally what we do is, we don't do this. Instead, we are going to take this value as the maximum shear force and we are going to design for the shear force. So by doing that, of course, we are committing some error. So whatever error we are committing is going to be on safer side. Instead of designing for lower shear force, we are designing for higher shear force. That's okay. Okay, that's what I am going to do. Therefore, maximum shear force at support. So I am going to call that as VUD equal to half the reaction, 18 multiplied by 6 divided by 2, that is equal to 54 kilonewton. Okay, once we have that shear force, we need to find out what is the nominal shear stress. Therefore, nominal shear stress tau V. Nominal shear stress is the shear stress caused due to the design shear force, equal to VUD multiplied by BD. Okay. So here, if you go to page number 72 of the code book, please go there. Okay. So if you look under 40.1, page 72, it says the nominal shear stress tau V equal to VU divided by BD. So that's what I have written here. So what is the value of VUD? That is 54 multiplied by 1000. Convert the value into Newton. B is 250 multiplied by 364 is the effective depth. So we are going to get the nominal shear stress equal to 0.59 Newton per millimeter square. Okay. This is the nominal shear stress caused due to the design load coming on the beam. However, the code says again on page number 72, if you go to 40.2.3, it says with shear reinforcement. So under no circumstances, even with shear reinforcement, shall the nominal shear stress in beam tau V exceed tau C max given in table 20. Okay. So, if you go to table 20 on page 73, what is tau C max value? For M20 concrete, it is 2.8 Newton per millimeter square. That is less than tau C max equal to 2.8 Newton per millimeter square. This is as per table 20, page 73. Okay. So, what in case this value exceeds 2.8 Newton per millimeter square? That means the shear is very high. Say for example, this is 3 Newton per millimeter square, which is greater than 2.8. In such cases, even if you provide shear reinforcement, the code says we should not allow the shear, nominal shear stress to exceed tau C max value. Then what is the solution? Then go back and redesign the section. Redesign the section means basically increase the sectional dimension, increase the depth, increase the width, okay, or increase both. So, once you increase the sectional dimension, then the entire design changes. Then you will have to check for tension, provide new tension area, okay, of new tension steel, go for again curtailment, check for AST maximum, AST minimum, etc. So, all that procedure should be repeated. In this case, yes, tau V is less than tau C max, then we are okay. That means, therefore, no redesign of the section is needed. Next, what is the next step? Next step is, as I explained in the previous classes, shear is going to be carried by concrete as well as the stirrups. First, we need to find out what is the design shear capacity of concrete. Okay, that depends on percentage of tension reinforcement at the section where we are considering the shear. Okay, refer page number 73, table 19. Depending on the percentage of tension reinforcement and the grade of concrete, you will get tau C value, that is the shear capacity or shear strength of concrete. Okay. So, we will proceed with that. So, to design, to check for shear, to find the design shear capacity or shear capacity of concrete. Okay. So, percentage of tension reinforcement at the support equal to AST divided by BD multiplied by 100. What is AST? That is the tension reinforcement at the support. How many tension reinforcements we have? We have 2 bars of 16 millimeter diameter, not 4, because we have curtailed 2 bars already. So it is 2 multiplied by pi by 4, 16 square. B is 250, D is 364 multiplied by 100, that is equal to 0.44% is the percentage of tension reinforcement. Okay. From table 9, page 72, for M20 concrete, for 0. ASTBD 100 tau C Newton per millimeter square, and for 0.25% steel, shear capacity of concrete is 0.36 Newton per millimeter square, that is shear strength of concrete. And for 0.50 percentage of tension steel, shear strength of concrete is 0.48 Newton per millimeter square. So what is the percentage here? It is 0.44. Of course, 0.44 comes between 0.25 and 0.50. So I need to find out what is the value for 0.44% steel. Therefore, shear strength or design shear strength of concrete is tau C equal to, it is 0.36 plus 0.50 minus 0.25, 0.44 minus 0.25, and 0.48 minus 0.36, that is tau C equal to 0.45 Newton per millimeter square. That is the shear strength of concrete, okay, or design shear strength of concrete. Okay. So once we have this, therefore design shear capacity or shear capacity of concrete equal to tau C BD, that is 0.45 multiplied by 250 multiplied by 364, that is equal to 40.95 kilonewton. Okay. So if you remember, so we call this as VC. Okay. See, out of, what is the value? Out of 54 kilonewton total shear, 40.95 kilonewton is carried by the concrete itself. So the remaining should be carried by the steel. Here it is stirrups. Therefore, shear to be carried by stirrups. So I am going to call that as V. Yes, I think V, not VC, VUC. And this is VUS equal to VUD minus VUC. So what is VUD? That is 54 kilonewton minus, I'm going to write here 54 kilonewton minus 40.95 kilonewton, that is equal to 13.05 kilonewton. So this is the shear to be carried by the reinforcement, that is stirrups. Okay. So we have open page number 70, again open page number 73 of the code book. VUS equal to 0.87 FYASV multiplied by D, and this is SV. So this is as per 40.4 and A, 40.4A, page 73. Page 73. So I am going to bring SV to this place and VUS to this place. Therefore, SV equal to 0.87 FYASV D divided by and VUS. So that is equal to 0.87. Fy is 415 multiplied by ASV. So it is the area of cross section of stirrups. Here we have 8 mm dia stirrups which are 2-legged. So it is 2. This is number of legs. Pi by 4 D square. Okay. And the effective depth is 364 divided by VUS. So that is the shear to be carried by the stirrups. How much is this? 13.05. I am going to convert this value into Newton. Okay, therefore SV equal to 1012 millimeter center to center. Okay. Check for minimum spacing. So here what we do is, so we got this value. Just because it says 1012 millimeter center to center or 1.012 meter center to center, it does not mean that we have to go ahead and provide that. No. So again, if you open page number 47 of the code book, 47 and 48, please open it. Under 26.5.1.5, it says the spacing should not exceed 0.75D and 300 millimeter. And also the code says the spacing should not exceed 0.75D and in no case it should exceed 300 millimeter. Those are the two conditions, that is the spacing should not exceed the following three values. Okay, what is that value? 0.75D, that is equal to 0.75 times D is 364, that is equal to 273 millimeter center to center. Okay, and 300 millimeter center to center. That is as per 26.5.1.5, page number 47. 26.5.1.5, page 47. Okay? And there is one more 26.1.6, 26.5.1.6. There you will see another condition. Minimum shear reinforcement in the form of stirrups shall be provided such that, so they have given a formula, that is ASV divided by BSV. ASV divided by BSV should be greater than equal to 0.4 divided by 0.87 Fy, where ASV is the area of cross section of the stirrups. So B is the width 250 millimeter, SV is the maximum spacing, okay, or the spacing, and Fy is of course 450 Newton per millimeter square. So after simplification, what we can do is, I can write this as SV, okay, less than equal to 0.87 Fy ASV divided by 0.4 B. Okay? So I am going to make use of that, and SV should be less than or at most equal to 0.87 Fy ASV divided by 0.4 B. Okay, this is as per 26.5.1.6, page number 48. 26.5.1.6, page number 48. Okay. So I am going to substitute all the values in this equation. That is, SV should be less than equal to 0.87 into 415 into ASV is 2 leg stirrups divided by 0.4 into 250, and the value is 363 millimeter center to center, should be less than equal to 363 millimeter center to center. See, according to the calculation, what was the value we got? 1012. But the code says the spacing should not exceed the following three values. What are those following three values? 273 millimeter center to center, another is 300 millimeter center to center, and this one 363 millimeter center to center. So in general, what we have to do is we have to take the least of the four values, design spacing and these three values. So out of these four values, what is the least? 273 millimeter center to center is the least value. So that is the maximum spacing of stirrups we have to provide. Therefore, this controls. Therefore, we can provide stirrups at 273 millimeter center to center, say 270 millimeter center to center. Okay, nobody is going to give this fractional value. So I am going to reduce the spacing from 273 to 270. That's okay. Is it clear to you? Thank you. ಇನ್ನೊಂದು ಮಾಡಬೇಕು. Hello, now let us go with check with deflection. That is check for deflection, I mean. So that is check for deflection. Please open page number 37 of the code book. Page number 37, that is 23.2.1, page 37 of the code book. So let me read out what that paragraph says. The vertical deflection limits may generally be assumed to be satisfied provided that the span to depth ratios are not greater than the values obtained as below. Okay, if I go to point A, so ours is a simply supported case. So simply supported case, it should not be greater than 20. Okay, it is not just 20, but we have to modify the value by multiplying that particular value with some modification factors. So if you go to point B, it says if the span is greater than 10 meter, then we have to multiply 20 by 10 divided by span. Okay. So here it does not come into picture because our span is 6 meter, which is less than 10 meter. Next, we will go to the next point C. It says depending on the area and the stress of steel for tension reinforcement, the values in A or B shall be modified by multiplying with the modification factor obtained as per figure 4. So this modification factor we are going to apply for tension steel. Next, if you go to the next point D, so depending on the area of compression reinforcement. So if we are providing compression reinforcement, that is in case of doubly reinforced section, so we have to give another modification factor, that is we have to multiply that 20 by another modification factor. And if you go to the next point, that is point E in the next page, so that modification factor for a flange section. Okay. On page 38, if you refer figure 4, so that modification factor we can get from this figure, figure 4, corresponding to point B. Okay. And for that we need to calculate certain value. Okay. So, and then we need to read the value of modification factor, that is for tension steel. If you go to figure 5 in the next page, that is page 39, okay, there is another table for modification factor for compression steel. If you go to figure 6, just below the figure 5, then we have to get the modification factor from figure 6. Okay. Figure 5 and figure 6 don't apply for us because we are not providing any compression reinforcement, and also ours is not a flange section. Okay, that is not a T section nor an L section. So ours is purely a singly reinforced rectangular section for which we need to give modification factor based on figure 4. Okay. So what it says is, as per the code, so for deflection condition to be satisfied, L by D ratio should be less than 20 multiplied by modification factors. So as I said, 3 modification factors: tension steel modification factor, compression steel modification factor, and flange section modification factor. So second and third don't apply. So I am going to apply only one modification factor. So that is L by D ratio should be less than 20 multiplied by FT, that is the modification factor for tension steel. Okay. So I need to find out what is FT. So for that, what I do is, on page 38 I am going to go to figure 4. So from that graph I am going to find out what is the modification factor. The first thing is I need to find out what is the percentage of tension steel we have provided, and the next thing I need to do is to find out what is Fs value. So to find out Fs value, if you have the table, just below the table, there is a formula Fs equal to 0.58 Fy multiplied by area of cross section of tension steel required divided by the area of cross section of tension steel provided. Okay, from that we can get Fs. Once we have the Fs, once we know the percentage of tension reinforcement, from that graph we can get the modification factor Ft value. So let us find out what is Ft. That is from table 4, page 38. So percentage of tension steel, equal to AST divided by BD multiplied by 100. So we have provided 4 bars of 16 millimeter diameter. Okay. So the area of 4 bars of 16 millimeter diameter is pi by 4 multiplied by 16 square multiplied by 4. B is 250 and D is the effective depth, which is 364, and multiplied by 100, we are going to get 0.88. Okay, that is the percentage of tension steel we have provided. Next, and Fs equal to 0.58 Fy, area of tension steel required divided by area of tension steel provided. Okay, this is the formula. So this is not Fs, Ft, capital Ft, sorry, Fs. So that is equal to 0.58 into 415. So what is the area of tension steel required? If you go back to the calculation of tension steel for flexure, if you go to that step, so check the value, we got the area of tension steel required as 742 millimeter square. Okay, then we divided this value, if you remember, by area of 16 millimeter diameter to get the number of bars. We got some 3.69 bars. However, we went ahead, we provided 4 bars. So area of tension steel provided is 4 multiplied by pi by 4, 16 square. Okay, this comes 804.25, this is 742 required, and after the calculation we are going to get this value equal to 222 Newton per millimeter square. That is the value of small Fs. Okay, now we have the percentage of tension steel, we have the value of Fs. Go to table or figure 4 on page 38 by referring figure 4 from page 38, modification factor for tension steel Ft equal to 1.1. That is percentage of tension steel on the horizontal axis. You see 0, 0.4, 0.8, 1.2, etc. So there you will have to go up to 0.88. Then you go vertically until you hit the value of Fs equal to 222. See, you cannot read that value exactly, but you can get the value approximately. Okay, get that and go horizontally and read the value. So we are going to get modification factor for tension steel, and we have called that value as Ft. Okay, and we got that value equal to 1.1. So now what I am going to do is I am going to substitute this value in this equation. If I call this equation as, say, equation A. So by substituting, the value of Ft in equation A we get L by D ratio should be less than 20 multiplied by Ft, which is 1.1, that should be less than 22. So L by D ratio should be less than 22. So then what is L by D? So that is, L is the effective span divided by D is the effective depth, okay, should be less than 22. That is equal to 16.48 is less than 22. So this condition is satisfied. Okay. Therefore, the deflection condition is satisfied. The deflection condition is satisfied. So there is one correction. For effective span, we have been calling as LE, not small l, but instead it is L suffix E. Okay. So this is the condition. Again, I will go back to the code on page 37. So let me read out under 23.2.1, page 37. The vertical deflection limits may generally be assumed to be satisfied, provided that the span to depth ratios are not greater than the value obtained as below. We have three values, one for cantilever, another simply supported, and the other for continuous beam. So ours is a case of simply supported beam. So L by D ratio should be less than 20, but if you go further to B paragraph, point B, point C, point D, it covers different cases. So for us, case C is applicable. That is, we have to give the modification factor for this value based on the percentage of steel. So we got that modification value 1.1. So we got this 22. So as per the code, whatever values LE by D should be less than 22. So what is the value of LE by D? 16 power 48. It is less than 22. So hence the deflection condition is satisfied. Okay. So in addition to that, we have got one more step, that is check for development length. Check for development length. This is as per, if you go to page number 44, 26.2.3.3. Okay. It says at least one-third the positive moment reinforcement in simple members and one-fourth the positive moment reinforcement in continuous members shall extend along the same face of the member into the support to a length equal to LD by 3. So I am going to explain what it is once I draw the figure. So let me find out what is LD first. Okay. So development length LD LD equal to 5 Fs 4 tau Bd. This is as per 26.2.1 page 42. Page 42, where phi is the diameter of the bar and Fs value equal to 0.87 Fy and tau Bd is obtained from 26.2.1.1 page 43. Okay. So by substituting all the values in this equation, therefore LD equal to phi is the dia of the bar. How much it is? 16 millimeter. Fs is 0.87 multiplied by 415. Okay. And 4. And what is tau Bd? Tau Bd is the design bond stress. So tau Bd is design bond stress. So this is obtained from 26.2.1.1 page 43. So if you go to that page 43, if you look at the top, so it says for grade of concrete M20, M25, M30, etc. design bond stress tau Bd is given. For M20 it is 1.2 and M25 1.4, okay, etc. So if you go above that table and read that line, design bond stress in limit state method for plain bars in tension shall be as below. So these values given in the table are for plain bars. Okay. Ours is twisted bars. Okay. That's why if you go below the table in the first column, it says for deformed bars. That is the bars we are going to use. Fe 415 is a deformed bar. Bars conforming to IS 1786, these values shall be increased by 60%. That means for M20 concrete, tau Bd value is 1.2. Okay, because we are using deformed bars, that value should be increased by 60%. That is, we are going to multiply that 1.2 value by 1.6. Okay, so here what I write is 1.2 is the value given in the table for plain concrete. Because ours is a deformed bar, we are increasing this value by 60%. So 692 millimeter is the development length. Therefore, LD by 3 equal to 692 by 3, that is equal to 231 millimeter. Okay. So with this, we are going to complete this design. I am going to explain once I write the figure what it is. Next, any design, this completes the design. Any design is incomplete without a drawing. So whatever you do in the design, finally that should be represented by a figure with all the required reinforcement details. Okay, and that drawing is going to be made use of in the execution of the work. So this is reinforcement details. Reinforcement details. I am going to show only a part of the beam. This is the support for this beam, one side of the support. And we have two bars continuing from here to the other end. And the remaining two bars, of course, we are going to cut here. That is called curtailment. And we are going to provide two nominal bars to anchor the stirrups, and we are going to provide stirrups at certain spacing as per the design. These are the stirrups. Okay, so I am going to take a section here. I am going to call this as section AA, and I am going to take one more section here. I am going to call that as section BB. So section AA looks like this. Section AA looks like this. That is we have 4 bars of 16 millimeter diameter. These are 8 millimeter diameter stirrups. This is section BB. Okay, this is the longitudinal section. This is the cross section AA. This is another cross section BB. So this is section AA and this is section BB. If you look here, section AA, we have 4 bars. And after some distance, we have curtailed 2 bars. So from to the left of the point of curtailment, if you take a section, you will only see 2 bars. So this is eight mm dia. You don't have to write millimeter. 8 dia, 2-legged stirrups. 2-legged stirrups at 270 millimeter center to center. So same as this. Okay, and 2 of 12 millimeter dia anchor bars. We are going to make use of these 2 bars to anchor the stirrups. So here we have 4 of 16 millimeter dia. So if we come here, it is 2 of 16 millimeter dia main steel. And if you look back the calculation, we have the curtailed bars here, and the location of the curtailed bar is located at a distance of 490 millimeter from the center of the support. Okay. Next, coming to LD by 3, which I discussed just now. So the code says at least 1/3 of the total reinforcement in a simply supported beam. At least 1/3 of the total reinforcement should be continued to the support, that is inside the support, for a distance equal to LD by 3. Is it clear to you? So if you take 4 bars, so 1/3 of 4 bars is 1.33 bars. So minimum at least 1/3, but we have continued 2 bars, that is 50% of the bars are continued and they have entered the support. So the distance, the development length should be at least equal to LD by 3, that is equal to 231 millimeter. Okay, this is the minimum one, or else I can write this as not less than 231. It may be more. So normally if we take say 300 millimeter wall, from the face of the support, we can continue this up to a distance of 260 millimeter, because by assuming 40 mm cover, side cover. So 260 mm, which is greater than 231 millimeter. So we are okay. What in case if this width is say 200 millimeter, that is the width of the support is 200 millimeter. If the width of the support is 200 millimeter, from the face of the support we have to extend the bar for a distance at least equal to 231 millimeter. In such cases, what we do is we come here. Of course, there is going to be a clear spacing, effective spacing of side cover, not spacing, effective side cover of how much? 40 mm. So 200 minus 40, that is 160 millimeter, and we need another 70 millimeter at least. For that, what we do is we can bend the bar and we can take the bar here. Of course, when you bend it, it will have a greater value. Okay. So, but here we can take that 70 as it is. So, if I take say 200, I am repeating, if you take the thickness of the wall as 200 millimeter, so from the face of the wall we can go up to a distance of 160 millimeter because we are giving a side effective cover of 40 mm. So at 160 millimeter, after going, you go up by 71 millimeter at least. That makes it 231 millimeter. That way, development length condition is satisfied. Is it clear to you? So this is one more thing I forgot to write. This is 4 of 16 dia. This is 2 of 16 dia. So 2 of 12 mm dia anchor bars, nominal. Okay, we are not going to consider these 2 bars for any strength calculation. Okay, this completes the design. Okay, thank you.